All right, so we've concluded 8.1 to 8.3, and this lesson will be after 8.3. And so the objective is to write a series in Sigma notation. And these are just some guidelines, meaning they're not like a step-by-step process, but so let's just take a look. Guideline number 1, write the explicit rule, okay, if it's arithmetic or geometric. In fact, I would try to follow this first, okay? So always check to see if it's arithmetic or geometric, and then if it is, just write the explicit rule. Sometimes you might have signs that alternate. In this case, you might want to use -1 to the n, -1 to the n plus 1, depending on if it's plus minus or minus plus. And if you have a fraction, you can try splitting up the rules for the fractions. And keep in mind that the n value doesn't always have to start at 0, okay? N can start at 0 or 1. And the very last thing, if all else fails, is look for a pattern, anything, okay? Perfect squares, perfect cubes, factorials. This is probably the hardest one, okay? So let's start with some basic examples, and then, of course, we'll take a look at the one that's more challenging. So take a look at this first example here. It says express in sigma notation. And immediately off the bat, I noticed that this is arithmetic. And so if it's arithmetic, right, you can write the rule. So again, right, a sub n is equal to a sub 1 plus n minus 1 times d. In this case, d is 2. Okay, so you can simplify that. You're going to get 7 plus 2n minus 2, which is just 2n plus 5. Okay, so 2n plus 5 is my rule. And I notice that I have 1, 2, 3, 4, 5, 6 terms. And let me write it in sigma notation. N is equal to 1 of 2n plus 5. And you can always check this rule, right? For n is equal to 1. 2 plus 5, does it give me 7? Yes, it does. For n is equal to 2, 2 times 2, which is 4. 4 plus 5, does it give me 9? Yes, it does. Okay, so this will be my final answer. Again, if it's a arithmetic sequence, you use the arithmetic explicit rule, and then you can count that there's literally 6 terms here. So if you take a look at example 1b, these numbers are almost identical to the previous example, 1a. Except the signs alternate. And so what I'm going to do is I'm going to write this rule again because I just completed this rule, right? It's, n is equal to 1 to 6 of 2n plus 5. And because it starts right here at positive and then it goes negative, what I'm going to do is put this in parentheses and simply write -1 to the n plus 1. Right? And again, you can check your rule, right? For n is equal to 1, well, n plus 1, 1 plus 1 is 2, -1 squared, well, that's going to give me a positive value, right? So you can plus 7 right here, and for n is equal to 2, right? This is for n is equal to 1. For n is equal to 2, 2 plus 1, that's 3, -1 cubed. Again, this value right here is going to be -9, okay? And so forth. The nice thing is you could always check your rule, and you should figure out for the very last one, n is 6, right? We should have a negative value, and we do, because -1 to the 6 plus 1 is -1 to the 7th, which will make this a -17, okay? So the trick right here is to include the -1 to the n plus 1 if the signs alternate. Okay, let's take a look at example 2. Off the top of my head, if I look at this, right, the sequence is kind of challenging, and you may not be able to see that if it's arithmetic or geometric, and it's neither. What I would do is follow guideline number 3, which is kind of split up the fractions and split up and write 2 separate rules, okay? So what I notice right here is in the numerator, I have an arithmetic sequence, and I'm just going to write my explicit rule. A sub n is equal to 3, first term. n minus 1 times d, the common difference is 8. and I'm going to simplify this. I'm going to get 8n minus 5. Okay, so my numerator is going to be 8n minus 5. And I'm going to start with n is equal to 1. I need to know how many terms there are, right? This is the last term of the sequence, so let's solve for n. Unlike the last example, right, I can actually count. This one I can't count. I actually have to solve for it. So if you divide 8 into 792, I believe you're going to get n is equal to 99. Okay, so n is equal to 1 to 99. And then you can do the same thing for the denominator. There's a separate rule for that. 10 plus a sub n is 10 plus n minus 1 times d. The d in this case is negative 3. And simplify that. 3n plus 3 plus 10. You're going to get negative 3n plus 13. Okay, so you should also check to see that n is equal to 1 to 99, your upper limit, if I plug in negative 284 over here. And you should check that n should equal 99 as well. Okay, so this is your final rule. The idea, again, is to split up the numerator and denominator. Is it always going to be true for fractions like that? No, it just depends. It just depends on what the actual sequence is provided. Okay, so again, following example 2a, right? This kind of looks exactly like the previous example, right? The numbers are the same, except there's a minus, right? There's a minus, and then it just goes to minus plus. And so that should signal in your head that maybe I need to just use what I had previously. And all I need to do is insert a negative 1, right? Because the signs kind of alternate. And because this time it starts at negative and n is equal to 1, I'm going to start at negative 1, not to the n plus 1, but negative 1 to the nth. And again, you can check, right? For n is equal to 1, right? Negative 1 to the 1, it should result in a negative value, which it does on the first term. For n is equal to 2, negative 1 squared should result in a positive value. And the second term right here for 11 over 7, that's positive. Okay, so this should be the rule because I already did all the work in part A. Sometimes all you need to insert is a negative 1 to the n, or in the previous example, negative 1 to the n plus 1, because it actually started as positive. Okay, so moving on, take a look at example 3a. Off the bat, right, I noticed that this is actually, in fact, a infinite geometric sequence or series. The first term, of course, is 1/3, and the common ratio to get from 1/3 to negative 2/9, divided by 1/3, of course, is just negative 2/3. Okay, so the common ratio is negative 2/3. My first term is 1/3, and my explicit rule for a geometric sequence or series is from n is equal to 1 to infinity, right? The dot, dot, dot indicates it goes on forever. First term times your common ratio, negative 2/3 to the n minus 1. So this one, very, very straightforward because this is geometric. And it's so I don't need to actually count the number of terms. All I did was write the explicit rule with the first term being 1/3. My common ratio is negative 2/3. Okay, so the nice thing is you could always check to see if your rule works. So I'll let you do that on your own. Okay, so this next sequence is also geometric, but it's not infinite, it's finite, right? So the first term is 8. The common ratio in this case is just negative 1/2. And so when you go from n is equal to 1, first term times the common ratio n minus 1, the only thing you need to do is figure out what n is. That's the only thing that was not given to you in this problem. You could try solving for it, right? 8 over 1024 is equal to 8 times negative 1/2 to the n minus 1. Right, this is just your geometric sequence, in case you're wondering. This is a sub n is equal to a sub 1 r to the n minus 1, right? I just substituted these values. But it's a little bit hard to solve this by hand. And so what you could do is I would just use a calculator to think hey, 2 raised to what power gives you 1024? And if you do the math, 2 to the 10th will give you 1024. Okay, so that means this value right here needs to be 10. And if it needs to be 10, right, n actually has to equal 11. Okay, so this one is just a little guess and check, which is fine because, again, this type of equation right here, exponential equation, is a little bit hard to solve by hand. Okay, so you can just guess and check, and is going to be 11, and that will be your final answer. Okay, so the idea is when writing a series in sigma notation, if it's arithmetic, write the arithmetic explicit rule. If it's geometric, as you can see in example 3, use the geometric explicit formula. The hard part, of course, is when we did a problem like example 2, right, where it was arithmetic in the numerator and denominator, where we kind of have to split the fraction. The hard part also is when it's neither arithmetic or geometric. Okay, so this one, example 4, I would just, like I said, for guideline number 5, just, try your best and see what kind of pattern you can come up with. And so this one, it's going to take a while if you don't notice off the bat, but what I'm going to do is I'm going to split up the fraction again. And what I can tell you is that these values right here in the denominator, they actually represent a special pattern. And like I said, it's just, you have to play around with these numbers. And at the end of the day, just, this being a short lesson, or I don't want this lesson to take up the whole hour, the denominator is just going to be n factorial, okay? So, well, how does that work? Well, this is right here, 3 factorial. This is 4 factorial, this is 5 factorial, this is 6 factorial. Okay, so that means this has to be 2 factorial, 1 factorial, and 0 factorial. So in my denominator, I'm actually going to start n is equal to 0, and this is going to be n factorial. Okay, so you can see that 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial is 720. But what about over here? Well, for the with this 1 right here, this value ultimately in the denominator, right, has to be 2. And because this is a 1 right here, right, I'm actually going to call this a 2 over 2, right? 2 over 2 will actually give you 1, okay? So that's, again, that takes a little bit of creativity. So this value right here is 1 factorial. That means this denominator right here has to be 1. And this denominator right here also has to be a 1, right? 0 factorial is 1. 1 factorial is 1. 2 factorial is 2. Again, this numerator right here on the third term has to be a 2, okay? And so we already have part of our problem. N is equal to 0 is our lower limit. N factorial is the denominator. And it's going to stop at 6, okay? And the very last thing is the numerator, and this just takes a lot of trial and error. At the end of the day, I'm just going to tell you in the numerator, it's just n squared minus 2. Okay, and you could always check to see if this works. You're like, wait, how does that work? For n is equal to 0, okay, 0 squared minus 2 over 0 factorial plus n is equal to 1. 1 factorial, sorry, this is, 1 squared minus 2 over 1 factorial, and so forth. You could always check it, see if it works. What is this? 2 squared minus 2 over 2 factorial. And if you just expand the first couple terms, right, you will get negative 2 over 1 plus negative 1 over 1 plus 4 minus, let's see, 2 squared is 4, 4 minus 2 is 2. 2 over 2, right? This is what I was talking about. This actually equals 1, which is what it was written here to begin with, and so forth. Okay, so these problems right here is just trial and error. And you literally just have to guess and check and hope for the best. Okay, so those problems I kind of skipped in the beginning of chapter 8. I want to cover that at the end of 8.3. So now that you have some tools in your toolkit, you're better able to handle these type of problems. And that will conclude this section on writing a series in sigma notation.